We'll do some more problems before we close this chapter on splitting field. The first problem we are going to do today is this. Let alpha be a 0 of p of x equal to x cube plus x square plus 1 in z2 of x. Then p of x splits z2 of alpha. z2 of alpha is the simple extension of alpha. Simple extension containing alpha. So to do this problem, we are going to use two previous results. The first one is from finite fields. If E is a field with p to the power of n elements for some prime p, then E contains precisely the zeros of x to the power of p to the power of n minus x. This is one result. And the second result is from a splitting field. If E is a splitting field over F, then every irreducible polynomial in f of x that has a 0 in E splits E. So we are going to use both the results to show this problem, to do this problem. So let us see what Z2 has, Z2 of alpha has. Z2 of alpha has all elements of the form A plus B alpha plus C alpha square. A, B, C in Z2. Because the degree of alpha over Z2 is 3. So if you replace A, B and C with zeros and 1, Z2 contains 0 and 1. The elements of this would be 0, 1, alpha, alpha square, 1 plus alpha, alpha plus alpha square plus 1, 1 plus alpha square. So Z2 of alpha contains, or Z2 of alpha is a field containing 8 elements, that is 2 to the power of cube, 2 to the power of 3 elements. So the elements of Z2 of alpha using this theorem are zeros of x to the power of 8 minus x. And that implies, so all the zeros of a to the power of minus x are in Z2 of alpha, meaning Z2 of alpha is a splitting field. Splitting field over Z2. Now, P of x equal to x cube plus x square plus 1 is irreducible. Because if you replace x by zeros and 1, you will never get 0 here in Z2 of x. What does that imply? So we have a splitting field and we have an irreducible element whose 0 is in the splitting field. And alpha is a 0 of P of x. And that implies P of x splits Z2 of alpha. The next problem is, let the degree of E over F is equal to 2. Then E is a splitting field of F. It's a very simple problem. So E is equal to 2 implies there exists an alpha in E minus F. If it is 1, then F is equal to E. If it is greater than 1, there should be at least one element in E which is not in F. So, because it is finite, E is algebraic over F. So, alpha is algebraic over E. Sorry, algebraic over F. That implies there exists a irreducible polynomial alpha comma F such that P of alpha is equal to 0. And the degree of P of x is equal to 2. Because the degree is 2 here. That means, so let degree of P of x equal to means it's a monopolynomial. So let P of x is equal to x square plus bx plus c for some b comma c in F. Since alpha is a 0 of P of x, x minus alpha is a factor of P of x. And that implies P of x equal to x minus alpha times x minus beta for some beta in E. Because this is a polynomial of degree 2 and this is a factor, definitely you can divide. And that implies beta is, say, conjugate of alpha, or beta is another 0 of P of x. Implies P of x splits E. So if you take any element outside F and inside E, then the irregular polynomial of that element splits E. And that implies E is a splitting field of F. So the next problem we are going to attempt is let F is a subfield of E, it's a subfield of F closure. E and F are fields. Then E is a splitting field if and only if it contains all conjugates over F in F closure of all of its elements. Meaning F closure F E. If you take any element here alpha, it conjugates also, any conjugate of alpha is also in E. Then E is a splitting field. Or if E is a splitting field, then any conjugate of any element of E is in E. So let us assume that there are two parts. So let us assume that let E be a splitting field and alpha belongs to E minus F. Because if it's inside F, it conjugates is itself, so you don't need to worry about it. If it's a splitting field, we have a result, the irreducible any irreducible polynomial, in particular the irreducible polynomial of alpha splits E. There is a result. The result is actually if E is a splitting field of F, then every irreducible polynomial in F of X splits E. What does this mean? This means every zero of the irreducible polynomial of alpha comma F are in E. Every irreducible polynomial. So every zero of that irreducible polynomial are in E. That means every conjugate of alpha is in E, because the zero of this polynomial is a conjugate of alpha, and that is the first part. If it's a splitting field, it contains all conjugates over F in F closure of all of its elements. See, alpha is an arbitrary element in E minus F, then every conjugate of alpha is in E. Now let us assume that let E contains all conjugate of every element in E. Now what we do is let tau be an automorphism See, one of the results we proved is the necessary and sufficient condition for a field to be splitting field. We want to show it's a splitting field based on some conditions. So we want to use that result to prove that E is a splitting field. So tau is a automorphism on F closure, and tau maps, tau is an automorphism, so tau should map every element in E to its conjugates. To take any element in E, tau should map to its conjugate, but it's the conjugate of every element, weight of every element, conjugates of every element are in E. That implies tau maps an element from E to an element in E. That means tau induces automorphism on E, and that implies E is a splitting field of. The reason why we went to an automorphism is because there is a necessary and sufficient condition for a field to be a splitting field. If an automorphism, every automorphism on F closure induces an automorphism on E, then E is a splitting field. And that is the result we used here. We'll do another problem. Show that the group of automorphism of Q of cube root of 2 comma I root 3 over Q of I root 3 is isomorphic to Z3 plus. This is a simple question if you use a result in group theory. Every group of order 3 is cyclic and isomorphic to Z3 comma plus. Z3 comma plus means 0, 1, 2, and the operation is, the binary operation is addition modulo 3. And we are going to use this because this is the simplest way to prove this. All we need to do is this contains 3 elements, then we are done. So what we have here is a Q and Q of I root 3 and Q of cube root of 2 comma I root 3. What does this mean? This is a group of automorphisms on Q of cube root of 2 comma I root 3, leaving I root 3 fixed. So G of q of cube root of 2 comma I root 3 over q of I root 3 is the group of all automorphism on q of cube root of 2 comma I root 3 leaving q of I root 3 fixed. So these automorphism, actually you have this, you are fixing the whole I root 3 here. So the only element that determines the automorphism is cube root of 2. So any automorphism any such automorphism is determined by the element cube root of 2. Meaning, and these automorphism should map cube root of 2 to its conjugates. Its conjugates are cube root of 2, cube root of 2 times minus 1 plus I root 3 by 2, cube root of 2 minus 1 minus I root 3 by 2. So this should match, this should, so the automorphisms are sigma 1 should map to sigma 1 should map cube root of 2 to cube root of 2, or sigma 2 should map to cube root of 2 to minus 1 plus I root 3 by 2 times cube root of 2, or sigma 3 cube root of 2 should map to minus 1 plus minus 1 minus I root 3 by 2 times cube root of 2. So G of cube root of 2 I root 3 over Q of I root 3 contains 3 elements. So any group with 3 elements are cyclic and isomorphic to Z3. All we need to prove is this contains 3 elements, and that's what we did. The next problem, let E be a splitting field of f of x in f of x or f. E be a splitting field of our f. This then any automorphism on E permutes the zeros of f of x. The meaning of this question is, if f of x is of degree n, and if alpha 1, alpha 2, dash dash alpha n are the zeros of f of x, then, and if sigma is an automorphism, sigma permutes the zeros of this polynomial. Meaning, what is a permutation on this? It's a map from this, bijective map from this to the same set. That is a permutation, a bijective map, meaning alpha 1 dash dash alpha 1, and here there will be some alpha j1, alpha j2 dash dash alpha jn. All these are same as this, meaning sigma maps alpha 1 to this, sigma maps alpha 2 to this. That is what you mean by sigma permutes the zeros of the function, the polynomial. It is actually very simple. Once you understand the problem, it's very simple. F of x splits E. That's the meaning of this. Implies every zeros of f of x belongs to E. So let degree of f of x be n, and alpha 1 dash dash alpha n be the zeros of f of x. Then alpha 1 dash dash alpha n are conjugates. So every automorphism on E should map every alpha j, alpha I to its conjugate. And that means every automorphism permutes the zeros of f of x. So we will do one more problem before we complete this chapter on splitting field. So that is, if P is a prime number, show that the degree of the splitting field of x to the power of p minus 1 over q is p minus 1. So we need to find out the splitting field of x to the power of p minus 1 and find the degree of that. So we are going to use a result that we established earlier in automorphisms. That is, for a prime P, if alpha is a 0 of x to the power of p minus 1 plus x to the power of p minus 2 plus dash 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 plus 1, that is equal to p of x, then the zeros of p of x, there are p minus 1 zeros for this polynomial. Zeros of the polynomial are alpha, alpha square, alpha to the power of p minus 1, and they all belong to the simple extension of alpha over q. So we are going to use this to solve this problem. X to the power of p minus 1 is equal to x minus 1 times x to the power of p minus 1 plus dash dash plus 1. And with that result, we know that if alpha is a 0 of x to the power of p minus 1 plus dash dash plus 1, then the zeros of this polynomial are alpha, alpha square, alpha to the power of minus 1, and they are distinct also. They are distinct and belong to q of alpha. A q of alpha, actually q of alpha, the degree of q of alpha, actually q of alpha is equal to a0 plus a1 alpha plus dash dash a p minus 2 alpha to the power of p minus 2. ai belongs to q, because it contains the polynomials in alpha whose degree is less than the degree of this irreducible polynomial. By the way, p of x is an irreducible polynomial. So the degree of q of alpha over q is equal to, the degree of this is p minus 1. Okay, and since all the zeros of x to the power of p minus 1 are in q alpha. See, q alpha, we say that q alpha contains the zeros of only x to the power of p minus 1, etc. But the other 0 is 1, and that is also a part of q of alpha. And that's why that's why I'm saying all the zeros of q to the power of p minus 1 are in q alpha. That is because 1 belongs to q of alpha. If all the zeros of q minus 1 are in q alpha, then q of alpha is the splitting field of x to the power of p minus 1. So the degree of the splitting field of x to the power of p minus 1 over q is p minus 1.